Salam and welcome. My name is Fatima Garba Yusuf and this is Electronics, and this is what we're going to do today. We're going to try and identify different material classes from a stress-strain graph plot. The question says, here are the stress-strain curves of tensile measurements of three different categories of metals: ceramics, polymers, and metals. Please name the category of metals each of the following curves A, B, and C. So we are supposed to determine which class of material does A belong to, which class of material does B belong to, as well as the class of material or the category of material that C belongs to. And because we were told that there are three different categories of materials, it simply means that A and B cannot be from the same category, nor can B and C be from the same category. Each of them has to be different. That is, one is metal, one is ceramic, and one is polymer. So how do we do this? There's no information, no values or anything. There's no value of Young's modulus or stress or strain or anything. So we are just supposed to use our knowledge of the characteristic properties of materials to determine the answer to this. Now, I can recall that in the previous video I actually showed a table where I tabulated the characteristic properties of polymers, of metals, and of ceramics, which can be used to actually determine which one is a polymer, which one is a metal, and which one is a ceramic. But you might actually know that, okay, ceramics are hard or metals are ductile, but you might not know how this is depicted on a stress-strain graph. And this is why I think before we solve this question, let us first look at how to identify the different regions in a stress-strain graph. So in a stress-strain graph, if you have a typical plot like this, so the first area from the 0 point, from the origin to point A is the proportional limits. So from the origin to this point, the material is actually elastic, and as soon as you remove the load, it will immediately go back to its original form. Then as it's increasing, there's an expansion. As it reaches B, then the elastic limit is reached, and it's also called the upper yield point. From then on, if you keep dragging the material, then it will reach the lower yield point. And as you continue applying the load or stretching it, it will reach a point where the breaking stress is reached. And after that, shortly after that, fracture occurs. So from the point O, the origin, to point B is where the elastic region is observed, while from point B to point E is where the plastic region is. That is, even though when you remove the load, it won't regain its exact original. Okay, so next we are going to determine, we already know that a stress-strain graph is a graph that shows the mechanical properties of materials. And what are those mechanical properties? Primarily, we have the ultimate stress, we have the ductility. It shows whether a material is ductile or not, it shows the strength of the material, it shows whether it's brittle or not, and so on and so forth. So let's see how these properties can be seen in a stress. Now, we already know that our Young's modulus is the slope of our graph. That's the rise over the run. That's the value of the difference in stress over the difference in strain. While, as I mentioned earlier in the previous graph, there is a point where after passing the elastic limits, there's a yield strength that serves as a shift between the elasticity and the plasticity, as is shown in this graph. Then there's the ultimate strength, which is the highest point of the graph, as shown in this plot. Then from that point, the material begins to neck, and then it leads to fracture. So next we're going to look at, before we move further, now from this graph, what I want us to understand is the Young's modulus actually shows the strength of the material, meaning the stronger the material, the greater the Young's modulus. And this is because the Young's modulus value is dependent on the stress value. That's the y-axis. So if we have a graph that is steep, that is, it has a high value of stress compared to a small value of strain, then it is implying that it is very strong, that is, it doesn't extend much even though you are applying much stress. So this is why the steeper the graph, the more it shows the strength. And typically when you are comparing metals, ceramics and polymers have the least strength, because as soon as you apply a force, a polymer will typically extend. While for metals, it depends on the type of metal, or maybe if you apply heat, that will lead to the softening of the metal and then it will extend. While for the ceramics, that's an almost no-go area, because just imagine stretching a piece of chinaware or a piece of a clay pot, it won't extend. So that's why ceramics typically have the greatest strength. And of course, when you are supposed to compare, then if you're trying to identify which one is a ceramic, then you should look at the one that has the steepest graph, that is, it has the highest Young's modulus. Next, we are going to talk about brittleness. Is the material brittle or is it ductile? And to know that, then we have to see how does the material absorb energy before fracture. Typically, a brittle material doesn't absorb much energy before fracture. That's why it doesn't even expand. And by not expanding, because it is not elastic, when you just reach a particular limit, it will just break or it will snap. While for a ductile material, you keep stretching it and stretching it, it will be adjusting, readjusting until it reaches the maximum before it will snap. And from this graph, as you can see, even though both of them have been truncated at the same level, showing the same ultimate strength, but because the first one, the one in red, is brittle, it doesn't have this long area of a graph. That is, it doesn't stretch much. That's why it's just a short area and then it fractures. As for the ductile material, because you are extending it and it is absorbing more energy, that's why it has a longer plots. So this can be further depicted by this T-shaped, bone-shaped samples. As you can see, for the brittle material, when you just apply the maximum stress, it will just fracture, as you can see for the red bone-shaped sample. While for the blue sample, as you keep applying the stress, it will have to extend a bit before it snaps. And maybe you can relate this better to what is contained in the graph. So now, even when we just take out these two properties, just the hardness, the strength, and ductility, we'll be able to actually have an idea of identifying which is which. If you see a strong material that is brittle, then you have an idea that, okay, it could be ceramic. If you have a soft material that is a bit strong but not too strong, then you can have an idea of what it is. And if you have a very soft material that is not strong, that is, it's not tough at all, then you have an idea of what material it is. So this is a plot that shows how you should expect your materials to be portrayed on a stress strain graph. First one is a steep plot close to the y-axis. It shows a material that is very hard and brittle. That is, it doesn't expand. It is not elastic, but it is very strong. Then the next one is a plot of a hard and strong material. That means it is hard, it's also strong, but it is not as brittle as the first one. Then the next shows a material that is hard and tough. That is, it is a bit ductile. That's why it will absorb some amount of energy, but it will probably not be as hard as the previous material. While the last plot shows a soft and tough material. By tough, it means it doesn't fracture easily, but because it is soft, that means it is not strong. Hence the low Young's modulus. Now from this, you can even pause this video and study this a lot, so that you will, even from this, you can have an idea of which of your plots that were given in that question is a ceramic, which is supposed to be in the lowest point, which is supposed to be at the top point. That is, if you combine the knowledge of these plots and the knowledge of your characteristics properties of materials, you'll be able to determine which one is, you'll be able to determine the category of each of the plots that were given to you in that question. But before that, let us finalize this. So we can summarize all this to show that a brittle material is the one that is close to the y-axis but it is very high. That's the one in red. Then a ductile material is strong but it's not tough. It's not soft. And because it is tough and strong, it is a bit less strong than the brittle material. And because it is ductile, it will absorb some energy before it fractures. As for the plastic material, it's typically quite soft and it's not as strong as the other categories of the materials. Hence, if we are going to expand our view, we can say that ceramics are typically the ones that you see close to the y-axis because they are brittle and strong. Then metals such as stainless steel are the ones that are just a little bit less strong than the ceramics but are typically more ductile. They are not as brittle as ceramics. Then we have the typical metals. Stainless steel is a bit above other metals because it has higher strength and it's an alloy. Then we have the bones and the ligaments in between the metals and the polymers. This polymer that was plotted in this graph is the ultra high molecular weight polyethylene. So as you can see, it is quite soft. It's not as strong as the others, but it is very ductile. Now, with this information, you can run back to your question and just answer it. So from this information that we're able to gather, what do you think is A? Is it a metal? Is it a ceramic? Or what is it? From the type of plots that we have, we can say that A is brittle. That is, it doesn't absorb energy before fracture, and then it is quite strong. It has high Young's modulus, right? And based on these characteristics, we can conclude that it's a ceramic. As for B, it is strong, but it's also tough. It doesn't break easily, and it's ductile. Now, based on these characteristics, we can say that it's a metal. While the last one, due to its low Young's modulus, because it will have a low slope, it can be said to be soft, flexible due to its high ductility, and based on these characteristics, you can say that it's a polymer. Understood? Even when you don't have the values for your Young's modulus, you can simply compare how your slope will be. Just look at this. It's not high. Then compare it with this. And compare it with this. This has a very high rise compared to a small run. So of course this is greater than this and this is greater than this. So with this, we've come to the end of this video. Stay tuned for other videos. Check out the other tutorials on different topics, subjects, and so on and so forth. Give us a thumbs up, leave your comments, and also like and subscribe to our channel. Thank you very much. See you in subsequent videos.